Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework for lesson 5.2.3. The M&Ms are all about independent and dependent events. Just remember, when they're independent events, one has absolutely no effect on the other event, like flipping a coin, rolling dice, spinning a spinner. Every time you do it, it's independent of the previous spin and any spin that's going to come thereafter. They're independent of each other. One does not affect the other. When you've got dependent events, that's where one of them does in fact affect the other outcome or the outcomes of the other events. So the typical example is drawing a card from a deck of cards. You've got a certain probability, and then if you do not put that card back in, now you've changed the numbers, and so that's going to change the probabilities. Same thing with pulling a marble out of a bag and not putting it back in, or reaching into a refrigerator and grabbing out a random can of soda. You are changing the numbers in the refrigerator, so that's going to change the probability. So that's what happens when you've got dependent events. One affects the probability of anything after that. All right, so let's go ahead and look at some different examples. We are to determine whether or not these situations are independent or dependent events. So spinning a 3 on a spinner after having just spun the 2. So every time you spin a spinner, each event or each time you spin is independent of any other. So you're never going to have spinning a 2 affect what your next outcome is going to be. Drawing a red 6 from a deck of cards after the 3 of spades has already been drawn. Okay, so let's just go ahead and think about this for a second. If you have drawn the 3 of spades, first of all, the probability of getting a 3 of spades is 1 out of 52. But after you pull it out of the deck, now there are no 3 of spades left in there, and there are only 51 cards remaining. So you can see how the probability has changed for the 3 of spades. Okay, so let's go ahead and look at this again. Drawing a red 6. Well, how many red 6s are there? There's 2 of them, right? Out of the 52 are red 6s. You got a 6 of hearts and a 6 of diamonds. If you pull out a 3 of spades, you haven't changed the number of red 6s, but you have changed the total number of cards in the deck. So this probability is different than that probability, which means that these are dependent events. And then drawing a face card from a deck of cards after a jack was drawn and then replaced. All right, so it was put back in. So the chances of getting a face card, what are there? 12 total face cards of the 52 cards. You pulled out a jack, but then you put it back in. So the next time you still have 12 out of 52, which makes it independent. And then D, this is the one, I don't really like this question because it's meant to trick you. Selecting a lemon lime soda if the person before you reaches into a cooler full of lemon lime sodas, removes it, and drinks it. So let's just pretend, like your refrigerator, why do I have that there? Let's pretend that your refrigerator has a total of 20 lemon lime sodas in it. What's the probability of getting a lemon lime soda if that's the only thing that's in there? It says the cooler is full of lemon lime sodas. It doesn't say that there's any other soda in there. So that's a probability of 1, right? Which means you're guaranteed of getting a lemon lime soda out of it. Well, after this person before you pulled out a lemon lime soda, now you've got 19 out of the 19 lemon lime sodas that are in there, which still means you're guaranteed. It did not change the probability, which makes it independent. Okay, so we're used to this whole idea that if you take something out and you replace it, it's always going to end up being a dependent kind of an event thing. Really, if you had some cola in there or you had some orange sodas in there and they came in and they pulled out a lemon lime soda and drank it, then that would absolutely change the probabilities of getting a cola or an orange soda after the fact. But the fact that they were all lemon lime sodas means that there was no change to the probability, which makes it independent. All right, what do we have going on here? Sky's ice cream shop is Mario's favorite place to get ice cream. Unfortunately, because he was late arriving there, his friends had already ordered. He did not know what they ordered for him. They told him that it was either a waffle cone or a sundae, and that the ice cream flavor was either apricot, chocolate, or blackberry. So if we're going to make a list of all the possible outcomes that we could have here, this is where it's nice to have an ordered table or a probability tree, which we will get into. This is setting you up for our future lessons about creating probability tables and probability trees. But we kind of saw it, how I organized the rock, paper, scissors game, and then the flipping of the two coins with Chris and Rachel in the previous lesson, how you make an organized list. And so what I would start with would be, okay, what are all the possibilities of ice cream desserts that you could get with a waffle cone? You could get waffle and apricot, you could get waffle and chocolate, or waffle and blackberry. What are all the possibilities where you would get sundae? Well, you could get the sundae with the apricot, sundae with the chocolate, or the sundae with the blackberry. So it turns out there are a total of 6 different combinations that you could get here. What is the probability that Mario will get something with apricot? Well, there's one with apricot, and there's one. So 2 out of the 6, which is the same, 2/6 is equal to 1/3, and we would always write that in simplest form. What's the probability that he will get a sundae? Well, looks like we got 3 sundaes there, right? 1, 2, 3. So 3 out of 6 is the same as 1/2. So what is the probability that he will get either something with chocolate? Okay, here's got chocolate, that's got chocolate, or a waffle cone with blackberry. Here's a waffle cone with blackberry. So that means you got 1, 2, 3 items that are what we would consider desired outcomes out of the 6 possible total outcomes. So 3 out of 6 is the same as 1/2. And then what's the probability he would get orange sherbet? Well, there is no option for orange sherbet, so that would be 0. All right, now we get into some review. On your paper, sketch this algebra tile shape shown at the right. Write expressions for both area and for perimeter, and then calculate the area and perimeter for each one of these values. So first things first, these are X tiles. These are single unit tiles. So this would be equal to X. This is 1, 1, 1. This is the entire X minus those 2 units right there. So that would be considered X minus 2. And this is 1, 1, 1, 1, 1, 1, 1, 1, 1. So by the time we finish all of this, we got 2 X's. And you got 1, 2, 3, minus 2 is 1, 3, 4, 5, 6, 7, 8, 9, 10. Wait, hold on for a second. Let's take these 2 and those 2 out of there. So that means you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. So 2x plus 10 represents the perimeter, and the area is pretty straightforward. You got 3 x's and 3 single unit tiles, so 3x plus 3. Now, for finding the actual perimeter, let's go ahead and plug 9 in here. So 2 times 9 is 18, plus 10 is 28. Here we're going to plug in 1/2, so 2 times 1/2 is 1, plus 10 is 11. And here we're going to plug in a 15. 2 times 15 is 30, plus 10 is 40. So these are all of your perimeters for these given side lengths. Okay? Now, if we want to prove that that's actually true, let's do this. Let's say if x was equal to 9, this would be a 9, right? And if x were equal to 9, this would be a 7. So you're going to have 9, 10, 11, 12, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Yes, that's what we said it would be. So this absolutely works. This is a valid strategy that you can use. We checked it 2 different ways and got the exact answer both ways, so we know that we're correct. Now let's plug in for area. The formula for area is 3x plus 3. So we're going to take 3 times 9 is 27, plus 3 is 30 square centimeters. Here, we're going to take half of 3, which is 1 1/2, and 1.5 plus 3 is 4.5. So that would be 4.5 square centimeters. And then 15 times 3 is 45, plus 3 is 48. All right, Ellen was or has made 29 note cards for her friends. She plans to send out a total of 40. What percentage of the cards has she finished? Okay, so she has finished 29 out of the 40 cards. And if we want to figure out what the percent is, and we're really asking for the percent, that would be a certain number out of 100. So if you want to, you can find a giant one where you multiply the top and the bottom times 2.5. Because I happen to know that 40 times 2.5 is equal to 100. But if you didn't know that, oops, stop that. If you weren't aware of that being your multiple, then, there's nothing wrong with cross multiplying. Let's say 40 times x is equal to 29 times 100, which is 2,900. And now if we divide that by 40, right? 40 times something equals 2,900. So 29 divided by 40 will tell you what that something is. Let's use our calculator for 2,900 divided by 40, and you get 72.5%. All right, and now we're going to combine like terms. So combining like terms, if you recall from last chapter, we're going to find all the terms that have the same variable raised to the same power, and we're going to add their coefficients together. If there is no variable, then we're just going to add the numbers together. So I'm going to go ahead and highlight all the terms that have the exact same variable parts and the same constant parts. So here you got 4 x's, put them together with 2 x's to make 6 x's, 7, a total of 8 x's here, and 3 and 2 makes 5. So the answer to this in simplest form, after you put all the x's together and all the 1's together, you get 8x plus 5. Here we're going to have 8x, and you're going to take away, that's a negative x there. So 8x minus 1x is 7x, and then 4 minus 3 is 1. So when you combine these guys with your 0 pairs, you're going to get 7x plus 1. In this case, we've got a total of 3 different types of terms. You got your x terms, you've got your constant terms, but you've also got your x squared terms. So I always like to start with the terms that have the greatest exponents. I'll start with the x squareds. You got 7 here and 7 there for a total of 14. You got 3 x's plus another 3 x's gives you 6 x's, and then you get 4 plus 4 equals 8. So by moving these terms around and combining like terms, we're able to write an expression with only 3 terms instead of 6 terms. This is in simplest form. And then for the last example, 5x's, there's 1x. You got a 4 and a 1, and then your x squared has no other x squared term to combine with. So we're going to leave that as it is. The 5x's and the 1x make 6x's, and the 4 and the 1 makes 5. So this idea of combining like terms is all about identifying the terms in your expression that have the same variable raised to the same power and adding the number parts together. That would be the coefficients of the variable terms is the number parts. So add the coefficients together, and you will have your terms in simplest form, your expressions completely simplified. And that is it. We are done with our homework. So I'm wondering, let's move on to our next activity.
Hey, feeling good.